It's not the exact minimal DFA, it's usually maybe a handful of extra states that don't want to make a difference.
So, announcements. We are 2 days removed from our exam study session in this class and 3 days removed from our first exam. So hopefully you're taking a look at the study guide, preparing your sheet of notes, and preparing to ask a bunch of questions on Thursday. I don't have a ton of content. That's actually not quite true. I do have some practice problems. And during our Thursday session, I will be revealing those practice problems for everyone to work on. And that way you can work on those practice problems in class. I can go over any of the solutions to that. I'll still be answering your questions, but then we can focus on the rest of them in office hours after class or office hours right before the exam for any of those practice problems that you'd like to do, see solutions to, get more experience or practice with. Feel free to reach out to me if you'd like additional practice problems and you don't have the book. I can go snip some extra practice problems of something that is exactly what you would like to target study, get some more practice with. Swing by my office hours and solve them on my board. I can let you know if I have any improvements to suggest for your process or the answer. What else? We have a drop dead deadline for the assignment tomorrow. Last night was the deadline to get feedback before the exam. Haven't had a chance to see and check back in with my grader. It sounded like he was making pretty good progress on assignment 1, but he needs to get started on assignment 2. So that's back to you before the exam. Last piece of information is this came together over the last couple of weeks, but if anyone remembers the hackathon from last year, we're doing it again this year. So May 17th, that's a Saturday. It's an all-day Saturday. You will be fed as well as you were last time. I think people who wanted to took home entire tubs of food or entire pizzas because we had so much food, and we actually have more funding this year than we did last year. We are very good at crunching budget, finding cheap options, and making sure instead of having just enough food, we have so much food that no one will leave hungry, and probably no one will be hungry for the next 3 days after the event. So feel free to show up. If does anyone know or not know what happens at a hackathon? I can describe what it is or what it does.
Like vaguely.
Yeah, so this is an opportunity for an all-day programming project. You come in with a group, you come in with an idea, you cannot have made any progress on that before the start of the day. And it's a competition for who can get the most done on that project or complete that project. And at the end of it, you have an opportunity to, no one has to do this, but you can present the end result of your day's worth of work in your group. And then monetary prizes will be awarded. I'm actually not 100% sure of the exact what the prizes are. We're still working through all of the logistical and legal hoops of what it takes to actually give people things. So we want to give people things. We have money to give people things. We just don't know exactly what that is going to be. So there will be prizes. And in general, it's just something really good for your resume or your portfolio. And it's great for networking as well. You'll meet other students, you'll meet professionals, since we bring in professionals to judge. And then there are prizes, so especially if you place, that would be something that is very good to know, or like something like prizes and awards sections of your resume. That's something that a lot of students have blank when they graduate. So if that is you, this would be a great opportunity for you to do that. And I will give anyone who attends, I don't care if you get something done, I just need you to sign up and show up, 10 extra credit points on the homework portion of the grade, which is not nothing because homework is where a lot of people struggle in the class.
Homework is where the heart is.
Yeah, exactly. So I think that's all over right now. Yeah.
Is there any reciprocal? Because I know I work that day, so I will not be able to make it. Could I get that extra credit in some other fashion?
I will try to come up with something. I don't know exactly what that looks like yet, but I do want that to be the case where if you can't make it, there will be other opportunities. Don't know exactly what that looks like yet, but especially if we reach later in the quarter and something hasn't happened, come back and talk to me about this or remind me of this and I will think of something.
So you can submit it online. I'm signing up, but I have a wedding to go to. So
Gotcha. Yeah, you can submit online. But it's hard to do it if you're actively working. So I have the poster here. I'm gonna put this up in my office. So if anyone's around for office hours and wants to know this in more detail or register based on the QR code, this will be around during both the class and after class and in my office after that. Other questions before we dive into the last little bit of the pumping lemma before we move past it? We're almost through it. I will be revealing the next assignment, I think, as well, this Wednesday. My guess is that I probably won't have it due for a couple weeks, though. But I do not want people to stress over getting started on the homework and an exam, and we'll see what the pace of the class looks like at that point. So one other thing I may do is do something like assign this homework, assign another homework next week, but then have the first homework due the week after that and the second homework due the week after that. So it'd be something like 2 assignments in 3 weeks. Do weeks 2 and 3, assign weeks 1 and 2. We'll see exactly, we just need to make sure we're keeping up with the course content. But I recognize that I've already put you through a bit of a grinder in terms of the amount of work this course has been. The second half of the class takes a step back from this pace.
I don't trust. There's a change in pace I don't trust.
There are a total of 6 assignments in the class, so we're already submitting the second of 6. So you've done a third of the homework deliverables at this point, and it has only been a fifth of the way. We're a fifth of the way through the class. For the most part, moving forward, assignments will be a little bit harder, but they'll be due every couple of weeks instead of every week as we start to transition from that. Okay. Last class, we finished our most complicated example where we had to split this down into cases to proceed with the pumping lemma proof. Were there any questions on this? So the language was AB to the N, A to the K, N is greater than K is greater than or equal to 0. We came up with a good choice for the string. We determined that, all right, there's this sequence of A's and B's that the X and Y portions of this have to come from. Then we just had to break it down into cases. The cases were starts with A, ends with A, starts with A, ends with B, starts with B, ends with A, starts with B, ends with B. And each one of those, you could combine a couple of them, like the starts with A, ends with A, starts with B, ends with B. Then you knew you were removing one more A than B or one more B than A, and that would have violated an aspect of the language. So you could combine those and target that with one, but then starts with A, ends with B, and starts with B, ends with A was a little bit more challenging to see. You're getting rid of at least one of those AB pairs, if that's the case. So then you tackle the N is greater than K portion because you selected the string AB to the M plus 1 A to the M. So if you get rid of a single AB, you're down to AB to the M A to the M, which is not in the language because N had to be greater than K, which it would no longer be. So that would be the 2 ways that you would prove or show that you split it into cases, solve it for both of those cases. You'll get a lot more practice with this on the homework. That's another reason I don't want this homework to be due for a couple of weeks, because it's going to take time to work through those pumping lemma problems. So that will be there. My recommendation is focus on the exam through Friday and then transition to thinking about the next homework. Last thing I want to talk about this is pitfalls in pumping lemma proofs, the kinds of mistakes that people will most frequently make. One I do see, and in fact I saw on my board yesterday, was trying to use the pumping lemma to show that a language is regular. Not only can this not be done, if a language is regular, then the pumping lemma will not be possible to set up and prove. But it's also way more work than the actual way that we show that a language is regular. What can we do to show that a language is regular? That it's way easier than the pumping lemma. Make a DFA. What else? NFA. What else? Regular grammar. Regular expression. Any of those 4, way easier than the pumping lemma. Any of those 4 will work. You don't need all of them, just any one of those will show and prove that a language is regular. If we were able to show that no string in the language could ever be pumped out, it's still not enough to show that the language is regular. So do not try this It is not worth your time or effort or energy. If you start with a string that's not in the language. So we know that when we pick that W, for the example above, before it was AB to the M plus one, A to the M. That string that we pick must be in the language. If you pick a string that is not in the language, any conclusion that we draw from this is invalid. If you proved it, it's still not a proof. If you failed to prove it, it doesn't show that the language is regular. So it does not work. As an example to this, if the language is A to the N such that N is a prime number, how would you come up with something to be able to try to latch onto this and prove that this language is not regular? One way that you might think to start this is something like, given M, let W equal A to the M. So player one, if we're playing the pumping lemon game, says, all right, here I have this M, the number of states in the associated DFA that represents A to the N such that N is a prime number. You as player two would try to say, given that M, I'm going to make a string that is A to the M. Why doesn't that work? What's the issue there? Yeah,
There are any number of M's that aren't prime and are, that's. not
Yes.
language.
so maybe the solution to this, we're making the proof by contradiction again and saying that, all right, whatever the player one selects as M, I will say make it A to the M such that M is whatever they pick. What if they pick something that's not prime? What if this language were to be regular and the number of states in that DFA weren't prime? Then you would be picking a string that is not prime as a way of carrying forward that proof. You can't do that. The string that you select here must be provable to be in the language that you start with.
Would you have to do like a, given M, let W to M, and then like such that M is prime, or like,
That would be
How
a
would you
better way to go
specify
about it, but you couldn't base it even off of,
a case?
yeah. Yeah, so the reason this one is difficult is because I'm actually not even sure this is context free. In fact, I'm
I don't know.
reaching very sure that this is not context free. And so you would need to use the context free pumping lemma in order to show that this is not context free. This is something that we can program, right? User enters a number and you answer yes or no, that number is prime. There exists an algorithm to do that. In fact, there exist multiple algorithms, efficient or not, to show this. Because it is computable, there exists some state machine that can be used to represent that language. It's just not regular. But the regular pumping lemma would also be able to show this is not regular by, this would be a really tough one to try to throw at you. I'm not gonna throw anything like this at you, but if you see something like this, don't start with a string that could possibly be in the language based on some possible M. So the issue is that M may not be prime. We can place a restriction, something like, now you could say M is going to be, we're gonna start with the next prime after M. That would work as a starting point. But it's still gonna be really difficult. I'm not gonna throw anything like this at you. If I did, it'd be the single most challenging something I threw at you on a homework. I would never throw this on an exam. Next one, any assumptions that you can make about how XYZ is decomposed? As an example, we still want to use prime number. Given M, let W be A to the K such that K is odd. If we continued saying subtracting an odd number of A's from a prime number means that XZ has an even number of A's and cannot be prime. Why is this bad? Any issues with this logic?
Wait, it's still it's still N is a prime number, right?
Yes,
Well, I mean, I feel like the obvious one is that two is a.
2 is prime, sure. There's still yet another, that is a very good idea, a good point.
That is an instant counterpoint to say no, because there is at least one prompt, and that is even therefore the argument doesn't work.
There's still a really big issue with this, even beyond that. Does anyone see that issue?
Is there still keys that are in and out of the language?
Yeah. So we can't say, we actually can't make the assumption that K is odd. That is an invalid assumption. Because K could be even, and we would need to be able to make a claim about even as well. So we cannot make any assumption like the number of A's in this string is odd. That's a restriction on the alphabet that we can't make.
Can you break it down to case, like, I have one case where K is odd, and this is my proof for that.
Yeah.
K is even.
Yeah, but you would need to make that even proof as well, because otherwise it's not complete.
If you have both cases, it's valid as long as you can show. In
Yes.
both cases, it doesn't work.
Yeah, you cannot restrict your domain beyond everything that you need to prove. Without showing that, breaking it down into cases and then showing that those cases, when unioned together, represent everything that you need to show. So those are my most commonly seen issues with proofs. There are probably more. This is just what I remembered and could write down ahead of this. So I would be happy to work with any of you as you're working through these on your homework, as you're preparing for exam 2. Remember, again, these are not going to be on exam 1. So you do not need to worry about this for the exam in 3 days. The cutoff for that was regular grammars. But we will, when we come back to exam 2 in a few weeks, this will be something, the thing that is furthest away in your memory from the date of that exam. So we will certainly need to revisit it. And we will certainly need to come back to some of these pitfalls as we get more practice closer to that exam. Last minute questions on pumping lemma before we move on to the next topic. I think it's just time for you to go off, get some experience, work on some problems, and come to me with the questions as you work on those. So we are not done for this. I just think we will work more effectively individually or in small groups as you come up with the questions from starting to get that practice.
Is there any specific place within, and like a compiler program where pumping lemma is absolutely vital?
Yes, because so regular languages show up most frequently in tokenizing as you're coming up with, all right, I have this stream of characters. I need to map these characters into tokens that have meaning. Do these characters, when they combine, represent something that is defined to be a variable? Do they represent a keyword in the language? Do they represent a legal mathematical expression? How do you tokenize in a way that comes together to create meaning? So as you do that, you will represent that as a regular language. You can use any regular grammar or state machine or something to be able to say, as I see these tokens and put them together, when I reach a final state, that token is now it's a token. Now we move on to the next one and read the next set of characters till we reach a final state. Bam, those goes into the next token, etc. So a pumping lemma would be something like this set of tokens, or this comes up to be, wait, this language is not regular. We want to be able to do this to show that something like the tokenizing step of any programming language is regular. If you were to come up with your own language in a way that the tokenizing was shown to be not regular, then you would have to fix that in order to be able to write a tokenizer for a compiler. Great question. We'll get down into those compiler steps probably about week 7 or 8, because there's still quite a bit of the different language classes to cover. So we're going to go cover the next one. All right, we've wrapped up everything from the first major language class, the regular language class. What is nice is I won't be throwing a bunch of new concepts at you for most of the rest of the quarter. It's going to be the same kinds of concepts. We're still going to be talking about grammars. We're still going to be talking about state machines. But now we're going to ease some of those restrictions to be able to allow the representation of more complex language classes. And more complex language classes have uses in terms of understanding and breaking down the existing programming languages or what you need to know to make your own. So now we've explored what it's like to show a language is not regular via the pumping lemma. Why would we care about languages that aren't regular? And in fact, there are just constructs in our programming languages that can't be captured in this. Sometimes we need to store not just state, but state plus a history, or state with some extra memory associated with it. So we need to define additional language classes. For instance, we showed that A to the n, B to the n was not a regular language. Why is A to the n, B to the n a really interesting language? Beyond just A's and B's, what does it represent in programming languages if you could make a replacement of A and B with something that you frequently see? Yeah.
Braces.
Braces, that's exactly right. So curly braces is a phenomenal way of representing something like A to the n, B to the n. So you have a long sequence of loops inside of loops inside of loops and an if statement inside of those nested loops, and then close all of that. You would see all of the opens before you see all of the closes. So now we can represent things like nesting control structures, nested if statements, loops, functions, and recursion. There's still a little piece of this that's not. You can open, open, close, close, something like that to show that there's some nest within that. But if we want to be able to reason about something like scope, then we want to be able to represent the concept of scope via some kind of language or some kind of grammar. And regular languages just could not do this. We needed to store how deep are we in this? Where is the position in the function that we just made a function call from that we need to go back to when we do something like end a function? So any of that is something that we just can't do with regular languages. So we need something more complicated than that to be able to represent that logic, as well as the logic of mathematical expressions. So we're going to get into context-free languages, and we will start by looking at context-free grammars. And the reason we started with automata at the regular language level, and we're starting with grammars at the context-free level, is that it actually starts getting more and more painful to visualize and to write out and make state machines as the language classes get larger. With context-free languages, the state machines for this actually look kind of gross for most of these. So I'm actually going to start out by looking at it from a grammar perspective. For review, this is great exam review. What were the restrictions that we placed on grammars to be able to make a regular grammar? Left linear or right linear? What was that, those definitions? Kind of what is a left linear grammar? What is a right linear grammar? Yeah.
Non-terminal terms have to be either on the left or the right side.
Yeah, and it's not it's a single term. We only have one non-terminal and then any number of terminals, or any number of terminals and then a single non-terminal. And that allows us to parse from left to right storing nothing, or from right to left storing nothing. If you can do that in one of those two directions, then what you have is a regular grammar. But that is excellent. That's exactly what we're looking for. Of course, context-free is a larger class of languages. What that means is there are more languages that are context-free than are regular. In fact, every regular language is context-free, but not every context-free language is regular. So it's a strictly larger class. You can envision this like a circle inside of another circle. All regular languages are context-free, but context-free had some additional languages that weren't regular. So exactly as that, every regular language is also context-free, but there are lots of context-free languages, an infinite number of them, in fact, that are not regular. So we're going to relax the restriction that we had about terminals and non-terminals from regular grammars. So non-terminals now do not have to appear on the far left or far right. They can appear in the middle. The reason we call this context free is that we don't need the context of all the terminals on the left side or the right side. We don't need that context to be able to make a decision. So let's take a look at an example context-free grammar. Here we go. 3 definitions for S. S can become A capital S A, could become B capital S B, or it could become lambda. Let's take a look at this. First, come up with some strings. What are sentences in this language? A. Sure.
BB,
BB. That can be done. What else?
empty string.
You can directly go to the empty string. Sure. Other people said something else? BB, is that right, that you said?
ABB.
ABBA.
BA.
What do we notice about this language? Any patterns emerging?
In
Palindrome.
So it's an even length palindrome?
That one, though, we did.
Yeah. This is that other one we did the other day that we showed wasn't regular. So now it's back with a really easy grammar when we relax that restriction of the non-terminals can come at the beginning or the end. This is the equivalent of recursing in the middle. Why is this something we couldn't do in a regular language? Beyond the fact that it just wasn't allowed in the grammar, why is this something that the concept of a regular language couldn't represent?
Store like extra data about surroundings to determine if it's valid. but then-
Yeah, this actually does a great way of counting things. If you force an A at the beginning and the end, now we don't have to count up the A's from left to right and know how many of them we had. We just know that when we place an A at the beginning and at the end and then recurse in the middle, that it's going to be a palindrome. It has to be by the nature of recursing in the middle. We also know that there are going to be an even number of A's and an even number of B's. There's no way to produce an odd number of A's or an odd number of B's. So we talked about the language it represents. This is actually WWR, which we said was an even length palindrome. So a string followed by that same string in reverse. Thinking about this as a regular grammar, we just determined that this is recursing in the middle. And there's no way to now parse this from left to right or right to left because we need to store the history of what we saw from the left so that we can map it on the right when we see it in reverse. There's just no way to do that without storing something. We'll actually come back to this. So this is a fascinating series of, this is a fascinating language. Because now this represents braces and or mathematical parentheses. All right, let's make a grammar for this language. Now we can have, very similar to early in the course, we can have non-terminals anywhere that we need them on the right-hand side of a production. So let's see if we can come up with a grammar for the language, A to the N, B to the M, such that we have a different number of A's and B's. How would we do that? Take a few minutes and think through it. So all the A's come first, all the B's come last. We just have to make sure that there aren't the same number of A's and B's when we terminate.
Be like a statement where it can be either A to the N, B to the N minus one, or B to the N plus one.
That would be one different. But what if we had a million B's and no A's? That's in the language,
Or even a million A's and no B's, that's also valid.
right? We have to make sure they're different. We cannot have the same number of A's followed by the same number of B's. Feel free to talk this out with people around you if you're feeling stuck. Got one? That would give you one more A or one more B. You get two more A's or two more B's.
I don't even know how to restrict this, so that
Yeah.
they're not the same. Without, like,
Here's
storing.
my thought, maybe I'll give you a hint or getting started. When I see this language, I break it down into something like either, I'm gonna write this as kind of like a regular expression, even though it's not regular. If we had any number of A's followed by the expression A to the n, B to the n. Or we had this concept of A to the n, B to the n, followed by, and it should be star, it should be plus. Does that help you? We have an even number of A's and B's, and then we add an arbitrary number, one or more A's at the beginning. It guarantees that it's not even and there were more A's than B's. The other option is we have an equal number of A's and B's, followed by at least one B, possibly many more.
Wouldn't no A's and then B's, would this also include that?
We probably need something that is Yeah, something like that. So this isn't totally complete. But it's how I envision the problem with regards to setting up a grammar, because we're in one of two worlds where how can we transition into, we would have some non-terminal that represents this idea, some non-terminal that represents this idea, and you could just OR this with lambda, and that would give you the ability to have no A's. Same here.
Grammars, we have to have it so that all either the right or left limb.
No, not anymore. You have the full, you think back to your homework 1 grammar problems. You have that level of power again. Some of this. Anyone have something that they've come up with?
Can I ask a question?
Yeah,
You have more non-terminals than just the starting one.
yes.
But also,
Yeah, an arbitrary number of total non-terminals. So I envision this as something that I'm gonna come up with these pairs where we did like the A to the N, B to the N portion of this. I'm gonna say either we have some A's followed by what I'm gonna call, I guess, double. I'm using something that is representing pairs, or maybe I should use P for pairs, D for either one of those will work. Or we have them appear, we have the doubles appear before the B's that are at the end, so it looks something like this. Again, we can use an arbitrary number of non-terminals. We don't even need to use terminals at this point. So the first thing I kind of want to define is this D, because the A and the B are going to be a little bit different from this. So I'll leave space for the A and the B, but the D down here is basically saying, let's add an A and a B and recurse in the middle. So we could do something like A, D, B in a way that recurses, recurses, recurses. And this is where we terminate the string. So this portion would represent something like A to the N, B to the N. But now we need there to be at least one more A or at least one more B. So how would we do that?
Rather than terminating them. That A goes to A and then A itself.
So that would be something that, since we want this A to appear before the D, we want to recurse on the left. So we want it actually doesn't really matter, but we'll do that. Say we can generate an arbitrary number of A's. Yeah,
What if you want, what if N or M to be of 0? Would that be the reciprocal string? Like
Yes.
One B or just one? A?
yes, we certainly want that to be possible. Is this complete? Right now we have infinite recursion, so how do we terminate this?
Can we end with a single A?
We want to end with a single A. If you put lambda here, this becomes the ability to do lambda and lambda, which would be N is equal to M at 0. So we need to terminate this by saying there's at least one A. This is how you're going to represent kind of the positive closure of something, to say we need at least one. This is the more than one, and this is what terminates with the last one. For B, We do almost exactly the same thing, except they're gonna be recursing here. The structure of the S says that they come after all of these, which is necessary. So now we could do B, B, or B. And that would work. Let's see if this works. Let's see if some path through this. So someone walk me through an example. We start with S. Which of these do we want to apply? A capital D or D capital B? A capital D, excellent. So already we've made a decision that says no string from this point can have more B's than A's. We're down the path where the final result to this is more A's than B's by this design and this grammar. From here, let's resolve this A. Which are we picking? Capital A or A?
Hey,
Let's have some fun. Capital A followed by this D. Let's resolve this A. What is it gonna be? Which one? A. Just the A, is that what I heard?
Terminated.
Yes, excellent. A, D. Excellent. Let's resolve this D now. So is this going to be A capital D B or lambda?
A capital D B.
Let's do it. So we have the two A's, then we have A capital D B. What do we want to do next?
lambda.
Terminate. Great. So we're going to have the three A's followed by a B. Done. Is this in that language?
Yes.
Yes. Can you envision any path through this that would generate a string that is not in this language? For every string that is in this language, is there an existing path through this grammar that produces it? Those are the two very important questions to ask if your grammar is complete. Yeah.
We're going with 0. Did you get that?
Get what equals 0?
So like n to 0 and like m to 1.
Yeah, so we just want a single B. Let's do it.
Just use the DB.
Yeah, we're gonna use DB to start. Then the D is gonna go straight to lambda, so we have B, and the B is gonna go to a single B. Done. So this represents more A's than B's, more B's than A's. This produces one or more A paired with the equal number. This produces one or more B's paired with an equal number of A's and B's. And this produces an equal number of A's and B's. But by forcing this A or B to be there, we need to be in one path or the other. Either the more A's than B's or the more B's than A's path. Questions on that generation? Questions on any of that logic? I like to try to walk you through my thought process for this, because when you just see this, it doesn't necessarily break down logically or easily into those cases. But I think if you can figure out, well, in order for this, there either needs to be more A's than B's or more B's than A's, that gives you a nice starting point for writing the grammar, breaking down that language into its intuitive components or unions of smaller languages that allow you to make those initial choices. I think that's what I put down. Just with hopefully clearer non-terminals. And sometimes the book doesn't really use the clearest non-terminal. I like clear variable names. So that would work. What about this?
You can't have more B's than A's.
Right.
Yeah.
So let's look at a grammar and try to determine what language is accepted by it. So here's an example. What language? Can we come up with some definition for the language that this represents? Is it? Intriguing. It's close, but it's not quite.
Can evaluate best.
Oh.
Yes,
I just had a quick question about, what were the two questions that you said we always need to ask ourselves?
yeah, for grammars. First is, can every string that is in the language be produced by the grammar via some path through the grammar? And the grammar must also be unable to produce every string that is not in the language.
This, I would assume for like race pairing.
Yes.
It allows for
Yeah.
that
Yep,
branching. like
Yes.
that.
yep. This is the mathematical expression generator.
Did you say that second one more time? Sorry.
Yeah, the grammar needs to not be able to produce any string that is not in the language. So it generates every string in the language and cannot generate any string not in the language. That's what's needed in order for it to represent that language. Everything that that language has in it can be derived. Everything that language does not have in it cannot be derived. So we could get anything that represents mathematical parentheses. We just replace the A with the open parenthesis, B with the closed parenthesis, and now this grammar can generate any arbitrarily complicated set of parentheses or set of curly braces.
You wrote that in braces.
It would be something like, we have a loop followed by a nested loop. For the second one, we'd have enter the first loop, enter the second loop, close the second loop, enter a new second loop, close the second loop, close the first loop. So it's great to see that there's a really simple grammatical definition of this concept, because it allows you to now, with something that's very simple, determine whether I see some syntactic set of parentheses. Is this a valid mathematical expression? At least the parentheses part of it. If we could map just the parentheses to this grammar, say, can this grammar generate this sequence of parentheses? Then we'd have a way of saying, yes, this represents legal parenthetical structure, or no, it does not. Same thing with curly braces. If you ever wonder how your IDE in real time is determining whether there's an extra curly brace or you're missing a curly brace, it's via something as simple as this grammar. It's mapping and saying, is the structure that you have right now with your curly braces, is that something that can be defined by this grammar or derived by this grammar? If yes, you're good, no red squigglies. If you can't, there's a red squiggly where it breaks. It was legal up until we reached this point. Either that's the termination point of your program, in which case it's expecting there to be an extra close. Or if there's an extra close and it got there's, wait, what is this closing? There's no opening that this is paired with, therefore red squiggly under that. It's actually quite simple logic compared to what you would expect. But because it can be easily mapped to a grammar like this, pretty easy to implement. We're unfortunately out of time already, so we will come back tomorrow and talk about leftmost and rightmost derivations, because it turns out that asking the question, is this string in this grammar? Can this grammar derive this string? It's actually a really difficult question. Why would you think that is? Think about that between today and tomorrow, and we'll come back and figure out why that is a difficult problem to answer in terms of the efficiency of this. How big is the search?
My guess now is, maybe since it's not a regular language, some form of memory space.
Yeah. All right, I'll have office hours starting now for anyone with questions. And since this is not Monday or Wednesday, I can stick around as late as I need to answer those questions.